we will take up thin cylinders and shells. What is the use of thin cylinders is that it is being used to carry liquids, gases, water, anything. So you have seen big tanga lorries and all, and on that you have got cylindrical shells, and in that it will be carrying kerosene, petrol or gas tank or something like that. So it is closed at both the ends. So it is a simple example of thin cylinders. So there is thick cylinders also, but how will you classify thick cylinders and thin cylinders? If the thickness of the particular cylinder is less than 1/20th of the diameter, you classify it as a thin cylinder. So thin cylinders can be analyzed due to the internal pressure acting inside the cylinder. So the thing is that you have got the gas or liquid being stored in the cylinder, and due to that there will be there will be pressure inside. So if you draw a particular cylinder like this, it has got a thickness like this, and it is subjected to internal pressure. So if you take the cross section, you have got the circular cross section, and the thickness is there, okay, this is the centroidal releasing. So this is the intensity of pressure P. So you have got the diameter D, thickness is T, and the length of the shell is L. So how will you analyze this? Due to that internal pressure, you have got the internal pressure. This is the cross section. This is the internal pressure, small p. So I am going to analyze this, what is happening on the wall of the cylinder due to this pressure. So let us take the section like this, and you consider an elemental strip over here at an angle theta from the vertical and subtending an angle d theta at the center. So the pressure acting on this particular section is, let us assume that this is delta P, pressure acting on this particular element. So this small angle is d theta, right? So how will you find out that pressure acting on that particular element? So we have seen that this particular cylinder, due to the internal pressure, can fail by bursting off. So this can burst off by bursting by this diameter. So you call the stress acting here as F. We call this stress F as F is known as Hoop stress or circumferential stress. This is known as Hoop stress or circumferential stress. So this is one stress which is acting on the wall of the cylinder in the diameter throughout the length of the cylinder. So I will just explain by showing you how this is being developed. Now let us just understand the derivation first. Now another thing is that it can also fail in the other direction also. That is, it can also fail by having a pressure acting like this. So if you take the longitudinal section like this, there will be a stress acting longitudinally along the circumference. So this stress is known as longitudinal stress. So you call it F naught, that is longitudinal stress. Okay, so you have got two types of stress being developed in the thin cylinder due to internal pressure. One is Hoop stress or circumferential stress, another one is longitudinal stress. So what happens here is, how will you analyze that due to this internal pressure? You are considering an element. So this delta P is equal to That is, what is the pressure acting on that element. What is the width of that element? Width of that element will be, if radius is r, you will have r delta theta as the width of this thing, and thickness is this is the r delta theta, and that is happening all throughout the length. So the area on which delta P is acting is r delta theta into L. If you take the circumference, you have an element like this, right? This is the width delta theta and this is the length L, right? So you have got delta P is equal to r delta theta into L. This is the area, and the intensity of pressure is small p instead of your sigma. Now what you are going to do is resolving the force in the vertical direction. This is your vertical direction. Resolving the forces, what you will have, you just take that delta P is acting there. This is delta P acting here, delta P cos theta. So you will have delta P cos theta is the force acting in the vertical direction. So you will have r d theta into L into P, small p, into cos theta, right? If you want to take, this is acting, you are taking theta from here. So if this particular cylinder is going to burst along this direction, it is bursting into two halves. So you will have theta being ranging from 0 to 90 on this side, similarly 0 to 90 on this side. So for the total force, what you have to do here is, total force is equal to integral 2 times 0 to pi by 2 into, I will this is P R L cos theta d theta, right? You can take the constants out. 2p RL, that is pressure is constant, radius is constant, length is constant. So integral 0 to pi by 2 cos theta d theta, right? So we will have PRL is nothing but PDL. Cos theta integration is sin theta. So you will have pi by 2 into 0. Sin pi by 2 is 1. So you will have the equation as PDL. This is actually, you call it as bursting force. Bursting force. So this is the force generated for the cylinder to burst or to fail. Or this is also, you can say that this is, if this is going to fail like that, this is the cross section. If you take it longitudinally, you can have this much width and we have got the length L. So it is actually, you call it this particular term as projected area. If you project this particular cylinder down, you can see a rectangular area D into L. So this is the terminology for bursting force, or you call it as actually P into projected area. Projected area. That is a bursting force.